There are moments in history that arrive with fanfare, broadcast to the entire world as they happen. And then there are moments so quiet that almost nobody notices them until years later. Right now, one of those moments is unfolding in the darkness beyond our solar system. Far from Earth, beyond every planet, beyond the last influence of the Sun, a lone spacecraft is approaching a line that nothing built by human hands has ever crossed before. It is not a border anyone can draw on a map. It is not the edge of a planet or the boundary of an orbit. It is simply a distance, so unimaginably vast that even light, the fastest thing in the universe, needs an entire day to travel across it. But before we continue this incredible journey, if you enjoy real science, space exploration, and stories backed by facts rather than hype, take a moment to subscribe to the channel. We're on the road to 1,000 subscribers, and your support genuinely helps us bring more stories like this every week. Now, let's continue. Later this year, Voyager 1 will reach that extraordinary distance. The spacecraft itself is surprisingly ordinary by modern standards. It is about the size of a small car and carries less computing power than the electronic key fob for a modern vehicle. It was launched before most people alive today were born. It was designed to survive for only 4 years. Instead, it has spent nearly half a century traveling farther than anything humanity has ever built. And now, just as it approaches the greatest distance ever reached by a functioning spacecraft, engineers on Earth are attempting something they have never tried before, a risky procedure with no second chance if it fails. This is not a story about history. It is a story unfolding right now, quietly, more than 15 billion miles away, while most of the world goes about its day without ever noticing. To understand why this moment matters, you first have to understand a number that sounds deceptively simple. 1 light day. At first, it sounds almost meaningless, just another enormous measurement among the countless enormous numbers used in astronomy. But the deeper you look, the more extraordinary it becomes. A light day is exactly what its name suggests. It is the distance light travels in 24 hours. Light races through space at roughly 186,000 miles every second, the fastest speed the laws of physics allow anything to travel. It reaches Earth from the Sun in about 8 minutes. It reaches the outer planets within a few hours. But traveling an entire light day means covering more than 16 billion miles. For almost the whole of human civilization, nothing we built ever came remotely close to traveling that far from home. Voyager 1 is about to change that. When it passes 16 billion miles from Earth later this year, something remarkable happens. A radio signal transmitted from Earth, traveling at the fastest speed physically possible, will need a full 24 hours just to reach the spacecraft, not to receive a reply, simply to arrive. Imagine an engineer sending a routine command on a Monday morning. Voyager 1 will not hear it until Tuesday. If the spacecraft answers immediately, Earth will not receive that reply until Wednesday. The simplest conversation possible, a single question followed by a single answer, will consume 2 entire days. No improvement in technology can change that. No faster computer, larger antenna, or better software can overcome it. The limitation is not engineering, it is physics. Nothing humanity has ever built has operated at such an extraordinary distance from the people responsible for it. And Voyager 1 has no intention of stopping once it reaches that milestone. Moving at more than 38,000 miles per hour, it will continue deeper into a region of space that had never contained a working scientific instrument before this tiny spacecraft arrived. But to understand why that journey matters so much, The story has to return to where it all began. In September 1977, a rocket climbed away from Kennedy Space Center carrying a spacecraft that few imagined would still be making headlines 50 years later. Its mission was straightforward: visit Jupiter, visit Saturn, take photographs, collect scientific measurements, then drift silently into space after roughly 4 years of work. No one expected anything more. Instead, Voyager 1 rewrote its own future. It swept past Jupiter in 1979, sending home the first truly close views of the giant planet's swirling storms and remarkable moons. Those images transformed humanity's understanding of the largest world in the solar system. A year later, it reached Saturn, using the gravity of both giant planets like enormous slingshots. Every flyby added more speed. Every encounter pushed it farther from the Sun than anyone had originally planned. What had begun as a modest planetary reconnaissance mission slowly evolved into something entirely different. By the end of the 1980s, Voyager 1 had become the most distant object humanity had ever launched. More remarkably, it was still working, still transmitting, still operating on hardware designed in an era that now feels almost prehistoric compared with modern computing. While generations of engineers came and went, Voyager simply kept flying. Its greatest achievement, however, still lay decades ahead. In August 2012, 35 years after launch, Voyager 1 crossed one of the most important boundaries in astronomy. It passed beyond the heliopause. That single sentence often disappears into scientific discussions without receiving the attention it deserves. The Sun is far more than a giant ball of light. It constantly throws out a stream of charged particles known as the solar wind. That invisible wind expands outward in every direction, creating an enormous protective bubble that surrounds our entire planetary system. Every planet, every moon, every asteroid, every spacecraft humanity had ever launched existed inside that bubble until Voyager 1 reached its edge. The heliopause marks the point where the outward pressure of the solar wind finally loses its battle against the pressure of interstellar space. It is not a symbolic boundary. It is a measurable physical one, lying roughly 120 times farther from the Sun than Earth. Crossing it means leaving the environment controlled by our own star and entering the environment controlled by the galaxy itself. Voyager 1 became the first human-made object ever to accomplish that journey. And ever since, it has continued sending information home from a place no instrument had ever explored before. Scientists expected the space beyond the heliopause to be quiet, a cold, empty region where charged particles drifted lazily through a largely featureless void. Instead, Voyager discovered something very different. Its instruments repeatedly detected a persistent signal within the surrounding plasma. Not a brief burst, not random noise, a continuous pattern that appeared again and again as the spacecraft traveled hundreds of millions of miles deeper into interstellar space. Researchers eventually realized that interstellar space was far more structured than theory had predicted. Rather than an empty void, it behaved like an environment with texture and activity, almost like weather on scales ranging from meters to millions of miles. For the first time, scientists were not imagining what interstellar space might be like. They were measuring it directly. And those measurements carried unexpected importance for Earth itself. The heliopause acts as a natural shield, deflecting a large fraction of the high-energy cosmic radiation constantly streaming through the galaxy from distant, long-dead stars. If the environment pressing against that shield is more energetic and more turbulent than expected, then new questions emerge about how consistently that protection works over immense periods of time. Those questions exist today because one aging spacecraft refused to stop working. Yet while Voyager 1 continued transforming science, another challenge was quietly growing inside the spacecraft itself. Not distance, power. For 35 years, Voyager 1 had done exactly what no machine before it ever had. It had traveled farther and farther from home, quietly leaving behind every planet, every familiar landmark, and every trace of the world that built it. Then, in August 2012, everything changed. Without fanfare or celebration, the little spacecraft crossed an invisible frontier that astronomers had spent decades studying. In that instant, Voyager 1 became the first human-made object in history to leave the Sun's domain and enter true interstellar space. It is a sentence people often hear without pausing to appreciate what it really means. Most people think of the Sun as nothing more than the source of Earth's light and warmth. But the Sun is constantly doing something else. Every second of every day, it throws an endless stream of electrically charged particles into space. This outflow, known as the solar wind, rushes outward in every direction, creating an enormous protective bubble that surrounds our entire solar system. Everything humanity has ever explored exists inside that bubble. Every planet, every moon, every asteroid, every spacecraft ever launched from Earth. For billions of kilometers, the Sun's influence dominates the surrounding space. But eventually, that influence reaches its limit. At the very edge of the solar wind lies a real, measurable boundary called the heliopause. It is roughly 120 times farther from the Sun than Earth is. Beyond that point, the outward pressure of the solar wind is no longer strong enough to resist the pressure of the galaxy itself. Crossing the heliopause is not symbolic. It means leaving the environment controlled by our own star and entering the environment governed by interstellar space. That is exactly what Voyager 1 accomplished in 2012. For more than a decade since then, the spacecraft has continued its lonely journey through the space between the stars, sending information back to Earth from a place no scientific instrument had ever explored directly. By itself, that was already one of the greatest engineering achievements in human history. Yet the real surprise came after the crossing. Before Voyager entered interstellar space, most physicists believed the region beyond the heliopause would be relatively quiet. A cold, thin, nearly featureless expanse, where charged particles drifted slowly through an almost empty void. Instead, Voyager began telling a very different story. Several years after crossing the boundary, one of its instruments detected something scientists had not expected to find: a persistent, narrow signal moving through the surrounding plasma. It wasn't a brief burst of interference or a random spike that could be dismissed as electronic noise. The signal kept appearing, year after year, million after million of miles farther from the Sun. As researchers analyzed the growing stream of data, an entirely new picture of interstellar space began to emerge. Rather than being smooth and uniform, the region beyond the heliopause possessed structure. It contained variations ranging from scales of only a few meters to distances stretching across millions of miles. Interstellar space behaved less like an empty void and more like a living environment filled with texture and motion that no one had ever been able to observe before, simply because no spacecraft had ever traveled there. That discovery reached far beyond academic curiosity. The heliopause acts as a protective shield, deflecting a large fraction of the high-energy cosmic radiation constantly streaming through the galaxy from distant, long-dead stars. Without that natural barrier, much more of that radiation would penetrate deep into the solar system. If the environment pressing against that shield is more energetic and turbulent than scientists once believed, an important question follows. How stable is that protection over immense periods of time? Today, nobody knows the complete answer. But the reason scientists can even ask that question is because one aging spacecraft has continued doing something nobody expected it to do. It has simply kept talking. Yet while Voyager 1 was rewriting our understanding of interstellar space, another story was quietly unfolding inside the spacecraft itself. It wasn't about distance anymore. It was about time. More specifically, it was about power. Unlike satellites orbiting Earth, Voyager 1 cannot rely on solar panels. At its incredible distance from the Sun, sunlight has become far too weak to produce useful electricity. Instead, the spacecraft depends on 3 radioisotope thermoelectric generators. These remarkable devices create electrical power by converting the heat released through the natural radioactive decay of plutonium-238. When Voyager 1 left Earth in 1977, those generators produced about 470 watts of electricity, enough to operate 10 scientific instruments while also powering the spacecraft's computers, communication systems, heaters, and attitude controls. But radioactive decay never stops. Every year, without exception, the generators lose roughly 4 watts of power. There is no way to refuel them, no possibility of repairing them, no method of slowing the process. Year after year, the available power simply continues to fall, bringing Voyager 1 steadily closer to the day when there will no longer be enough electricity to keep even its remaining systems alive. Nearly half a century after Voyager 1 began its journey, the greatest challenge facing the mission was no longer distance. It was time, or more precisely, the slow, unstoppable loss of power. Every year that passed quietly reduced the spacecraft's ability to keep itself alive. The countdown was invisible, predictable, and impossible to stop. It had become the single defining reality of the entire mission. When Voyager 1 left Earth in 1977, it carried 10 scientific instruments, each built to study a different part of the solar system. Together, they formed one of the most ambitious scientific payloads ever launched. Today, most of them are silent. Not because they failed, not because they wore out. They were switched off deliberately. One by one, NASA's engineers made painful decisions, sacrificing instruments that still worked, so the spacecraft itself could survive a little longer. Every shutdown was a trade-off, buying precious months or years for the systems that remained. And almost every one of those decisions was permanent. Once an instrument was shut down because the spacecraft could no longer spare the electricity to run it, there was usually no bringing it back. Then came one of the hardest choices the mission team had faced in decades. Earlier this year, reality finally caught up with them. In April, engineers sent a command across billions of miles instructing Voyager 1 to switch off its low-energy charged particles instrument. For nearly 50 years, that instrument had quietly measured the ions, electrons, and cosmic rays surrounding the spacecraft. Its observations had played a direct role in confirming the historic moment when Voyager 1 crossed beyond the heliopause and entered interstellar space. Nothing was wrong with it. It still worked, but keeping it alive had become a luxury the spacecraft could no longer afford. The decision followed an unexpected drop in available electrical power caused by a routine spacecraft maneuver earlier in the year. The decrease brought Voyager dangerously close to triggering its automatic fault protection system, designed to shut down spacecraft systems on its own if power demand ever exceeded what the aging generators could supply. Allowing the spacecraft to make those decisions automatically was a risk the team was unwilling to take. Instead, they acted first. They chose exactly which system would go dark, and exactly when it would happen. After nearly half a century of faithful service, the instrument fell silent, not because it had failed, but because the spacecraft needed its remaining energy somewhere else. When the shutdown was complete, Voyager 1 was left with only two scientific instruments still operating. One was the plasma wave subsystem, quietly listening to tiny oscillations moving through the charged particles of interstellar space. The other was a magnetometer, continuously measuring the invisible magnetic fields surrounding the spacecraft as it traveled through a region no other instrument had ever explored. That was all that remained. Just two instruments aboard a spacecraft that had once carried 10. Yet despite everything, Voyager 1 continued working. It was still transmitting, still collecting scientific data, still operating farther from Earth than any object humanity had ever built, all while surviving on a shrinking power supply that grew smaller every single year. It would have been easy to think this was simply the beginning of the end, but the engineers responsible for Voyager 1 refused to accept that. Instead of watching the spacecraft slowly fade away, they began preparing something that had never been attempted before. Inside NASA's Jet Propulsion Laboratory, the plan earned an unusual nickname. They called it the Big Bang. The name had nothing to do with explosions. It described the scale of the change. Normally, engineers would modify one spacecraft system at a time, carefully checking each change before moving to the next. That slow, cautious approach had kept Voyager alive for decades. This time, they intended to do the opposite. Several systems would be changed together during one carefully coordinated operation. Some components would be shut down completely. Others would be replaced with lower power alternatives capable of performing the same essential jobs while consuming less electricity. For the first time since Voyager 1 left Earth, the spacecraft's entire power configuration would be reorganized in a single attempt. The strategy sounded risky because it was. Whenever electrical systems are reconfigured, there is an unstable period when the spacecraft exists somewhere between its old configuration and its new one. Those brief moments are dangerous. They can confuse onboard systems. More importantly, they can trigger Voyager's automatic fault protection, the very safeguard the engineers had narrowly avoided activating earlier in the year. Paradoxically, that danger was exactly why everything had to happen at once. The less time the spacecraft spent in that unstable state, the lower the chance that its own protection system would mistake the planned changes for a serious malfunction. But there was another reason every decision carried enormous weight. Unlike a modern spacecraft orbiting Earth, Voyager 1 cannot be repaired. No astronaut can reach it. No engineer can plug in a diagnostic cable. Every command travels billions of miles before arriving. If one instruction is wrong, there may never be an opportunity to correct it. One mistake could permanently disable part, or even all, of the mission. The engineers know that every time they press send, adding to the challenge is the spacecraft itself. Voyager 1 was designed using engineering practices and programming conventions from the early 1970s, long before modern aerospace software existed. Most of the people who originally designed those systems have long since retired. Some are no longer alive. The engineers caring for Voyager today have spent years learning an almost forgotten language of spacecraft engineering, studying decades-old documentation, and mastering design principles that belong to another era. That knowledge cannot simply be handed to someone else. It lives in the experience of a remarkably small group of specialists who have devoted years to understanding exactly how this extraordinary machine thinks.